The last concept that we need to cover on topic 4.3 for the standard model is about symmetry in particle interactions. Unfortunately, this dot point from the syllabus, it's kind of like a bad research question in that it's not very specific. There are a number of different types of symmetry that we could look at, and there's a few different aspects of significance that we could talk about. So I'm going to go with the one that I think is the most significant. And before we do that though, we need to talk about what symmetry actually is. Now, you might be used to symmetry as being that idea where things look the same either side, so imagine butterfly wings, or if you think about it in terms of maths, being able to divide a shape so that it appears the same on both sides of that divide. In physics it's a bit different to that. Symmetry is the concept that if you take a system and apply a transformation to it, and by a transformation we could mean that it's something like moving it to a different place and using the system in a different time, that system will remain unchanged after a transformation is applied to it. Now that wording is a little bit can be a bit tricky to process exactly what that means. So to put it in context, let's consider the system, and sort of saying that in inverted commas, of the production of the hydrogen spectrum. So that's to do with hydrogen being energized and producing those colors of light that we see. That system can be observed in a few different places. And two of those places that are particularly significant are in distant stars and also in our own sun. Now, the reason why that's significant is that the transformations that we're looking at here, being spatial translation, so that means moving through space, so our sun is in a very different part of space to other distant stars, and secondly, the time translation, so the fact that what we're seeing from distant stars is from a long time ago, they don't actually change the system. So we still see that same spectrum of hydrogen being produced, and that means that we have symmetry in spatial translation and in time translation. So that's just an example. Another way to think of this is that the laws of physics apply everywhere in the universe. So it doesn't matter where you go, it doesn't matter when you go, those laws will still apply. Applying that more specifically to particle physics, there are three that we're going to have a look at, not in much detail, but just to tie back into this idea of symmetry. And these three are fairly significant when taken together. So we'll look at each of them individually first and then consider what they mean together. So the first is charge symmetry, and what that means is that for a particle interaction, reversing the charges as well as other quantum numbers. So by other quantum numbers we mean things like the spin, the baryon number, the meson number, and if we reverse those things, is not going to affect the particle interaction that we're dealing with. So that means that the particle interaction will still occur even if we reverse all of those particular properties. We've already had a brief look at this in a couple of situations, but the one that we're going to focus on again is the decay of a positive pion. We've seen that decays into a positive muon, that's an anti-muon, and also a muon neutrino. Now, if we reverse the charges, reverse the quantum numbers, that really means that we're looking at all of the antiparticles of these particles, and so we end up with this as the interaction, and both of those equations make sense, they both work, the interaction still works in that context. So that's charge symmetry. The second one is known as parity symmetry. And parity symmetry, we're not going to go into this one in much detail at all. It really just means that inverting spatial coordinates, so if we take sort of x, y and z coordinates, so inverting those spatial coordinates of the universe does not actually affect particle interaction. Another way to think of that is kind of to sort of look at the mirror image. So flipping everything in the x, y and z axes, we're going to see everything being mirror reversed effectively. We'll come back to that when we consider all three of these together. And finally is the time reversal symmetry. Now you might be looking at this one and thinking, well hang on, how can time be reversed? We can't move backwards in time. And on a sort of a global scale, so looking at large scale systems, you'd be right. But when we start to look at a fundamental scale, so looking at particle interactions, so on that fundamental level, particle interactions are reversible in time. So that really means that we can take reactants and products and reverse them. So products become reactants and vice versa. And so they're going to be reversible in time. So those three symmetries, as I said, are the most important when it comes to particle interactions. We'll now have a look at what the significance of those three are. And the first thing to state here is that we've actually seen violations of each of those symmetries. So it kind of seems a bit strange. We've just talked about how important they are, and then we're saying straight away that they have been violated. And when we say that they've been violated, what we mean is that there have been particle interactions that have been observed that don't actually show charge symmetry. So you can't swap out the charges and the all of the other quantum numbers and have an interaction that still works. Likewise, we don't see time reversal where the interaction can happen in either direction. Having said that, the vast majority of interactions we see do obey those symmetries, but because there are some that don't, because there have been some violations, they are not considered to be universal laws of nature. And a universal law of nature is something that can be applied, as it suggests, universally, so anywhere in the universe. Something like Newton's law of gravitation would be universal. So we see that attraction of masses anywhere in the universe, anywhere that we look. We can see stars being gravitationally attracted, galaxies being gravitationally attracted, and so on and so forth. So while they're not laws of nature, the real significance comes in when we think about the simultaneous transformations of all three of those. And that's referred to as the CPT symmetry. So C for charge, P for parity, and T for time. So applying all three of those, this is an exact symmetry of nature. And what that means is that there have been no observations of all three of those simultaneously being applied where violations have been observed. So applies universally. Applying all of those three simultaneously means that we will have first of all, a mirror image of our universe. So that's looking at the parity symmetry. If we then look at the charge symmetry, that would mean that this mirror image would contain predominantly antimatter, whereas our universe contains matter. And finally, considering the time reversal, that would mean that all of the momentums, so when we're talking momentum, we're really talking about mass times velocity, and so if time is reversed, then velocity will likewise be reversed. So all of those momentums reversed, and as I said, that's due to time reversal. That universe would evolve under the same laws of physics as our universe. So we now have a potential universe that in all ways is the opposite of ours, with charges reversed, with directions reversed, with time reversed, behaving in exactly the same ways as we are used to with all of the physical laws that we know. So fairly significant application of symmetry to particle interactions. And just a reminder, for this particular idea, you just need to be able to describe that significance. So the symmetry that's involved with particle interactions means that we could have this alternate universe that's opposite to ours.